Hello everyone, welcome back to another component showcase video, and today I want to show you some new merging technology that I've been developing. And I just want to say it's not completely optimized, but it is functional and it's quite a good proof of concept. And it is a merger that can process 3 boxes at a time instead of 2. So you're basically unloading 2 Shoggle boxes into one, and this has some interesting implications for particular kinds of input conditions. I'll talk about that a bit later. But yeah, without further ado, I'll just show you it. So I've just switched it on and you can see we are merging 2 boxes into one. Check it out, that is double hopper speed loading. And I haven't put too many boxes in here, so it should, too many items in, so it shouldn't be too long before it works. And it just basically sends all of the boxes into a single item stream. It gets quite complicated if you don't do that. Yeah, so that it does work, and it's quite interesting because there's actually 3 conditions for ending the merge operation. And one of them is when basically both shulker boxes run out of items, but because we've ordered them in such a way, we know that the second most full one is always here, so you can basically just read from this comparator. The other condition is that this box basically just fills up, and so basically those are the 2 conditions for like normal merging. But the third condition is just like an additional optimization, and that's when the least full box empties. And it's because we kind of assume that, you know, all of the mergers are operational at any given time, and so because of that, it's sort of deemed to be optimal to, you know, whenever we have 3 boxes that have become 2 effectively, we want to get rid of those and replace them with 3 boxes. So, you know, you can quite easily remove that optimization, but that's just there. You also might have noticed that I sort of switched it on manually to begin with. And the reason for that is just because of an edge case. So you'll notice at the top that we basically send the most and second full shulker box through the same, through the same dropper line. And basically just if it happens at if an unlock happens at exactly the wrong moment, or a lock, then it can mean that one of those boxes can go into a different merge than the other one. And so, basically we just have a kind of global line latch thing. This rail just provides an additional update here, to sort out that edge case. I did consider using a third dropper line, but it just kind of adds to the profile of this quite significantly. You have to add like 2 or 3 additional vert blocks on the sort of vertical scale, so I just thought I'd go for this instead. But yeah, that is the design. It might also look like there's kind of a lot of random like 8 game tick repeaters, but it is actually timed quite precisely, because you can have edge cases where you also might have noticed that the clock speed was quite slow, and that's because in the case where it empties, then it's important that the hopper kind of unloads all the items into the first box, and in the case where you get a full box, it's important that all of the items go into the second box and not the third box, because that just produces additional partials, which reduces efficiency. It's also worth mentioning that this works with just 2 boxes, so if you have 2 boxes coming in rather than 3, it will be able to handle that as well. And so this means you can also sort of an additional, not necessarily benefit, but an effect is that you can process a wider range of boxes. So basically any situation where the number of boxes has a remainder that just isn't 1, essentially, you'll be able to process those just straight away. There won't be any boxes in queue effectively, which is quite nice, because normally with merging, if you have an odd number of boxes, then you have to wait to process the last one. So that's just another interesting effect. Now you might also be wondering how we are able to tell, how we're able to order the 3 boxes. So this is relatively straightforward to do when you have 2 boxes. You just compare 2 of them and then, send them through different streams or whatever. But it gets a bit more complicated with 3. One option is just to, determine the signal strength of all 3 and then just kind of get rid of them in order. But another way is using a kind of sort of strange comparator logic situation. And you can see here, this basically will just, depending on which one of these lamps is lit, will tell you which one is the most full box at any given time. So you can see here, this is the most full. But if I sort of get rid of this, now this one is the most full, and then that one will light up, and then the same for the middle. And so the idea is that we basically just receive 3 boxes, and then it will be like, okay, this one's the most full, so we'll break this. And then this obviously needs to update. That doesn't happen in reality, and then now you can see the one on the right is the most full, so we break that, and then it will just break the final box. So in order, we can basically send these boxes, and that way we can most effectively distribute the boxes to the mergers. The other challenge when trying to do merging like this is we need to actually be able to get the boxes in the first place. How do we get the 3 boxes to call to the mergers? And there's a few different ways you can do this. The solution I used was, I think, probably relatively atypical, but the idea is that you just have, you basically just have an S file. There's a bit of a strange S file I've made. It's an 8 game tick one, but it's quite interesting because it doesn't have the minimum number of hoppers, it has 3 here. And that's because you need to be able to lock this top hopper, which only really works when you have like this kind of system. And the reason you need to be able to lock the top hopper is because you have to use what's called a kind of double pass lock system. And I made a video about this ages ago, but the idea is that you can, by sort of strategically locking and unlocking the SVARs, you can basically make it so each slice has a different item type, which doesn't matter too much in this context, but it actually it also does to some extent. And the idea is that we're basically taking just a completely continuous input from splitters or from another approach, and basically just, key genning and then storing. And we basically have this big stack of chests. That's why this thing is quite big, which will just store one item type. And the idea is that because you can take in boxes faster than you can send them off to the mergers, because in reality you only have a finite number of mergers, then it seems reasonable to want a kind of merging storage where you just store up loads of boxes from each item type and store them. And the other reason you want to do this is because it becomes difficult to use a kind of ordering system, although this does keep the order to some extent, because we could be taking either 3 or 2 boxes, and that's not really determined beforehand unless using an optimization algorithm, which we'll talk about later. It makes sense to just kind of have a storage rather than just a kind of ordered pair silo, which is independent of item type. Anyway, so that's the motivation for this. And then the idea is that you have a bunch of chests, and again, lots of edge cases. I won't go into all of them. But the idea is that basically that they come down to this dropper, and depending on the contents of the dropper, it will change this item stream. So if you have 0, 1, well, if you have 0, 1, it won't do anything. But if you have 2 or more, so 2 or 3 or whatever, then it will remove this ice block. And what that means is that basically the shulker boxes will be dispensed down into this stream, which gets sent to the mergers. And so we have a kind of cool system where, and again, another edge case can come up here, that's why we have a piston. But you have a cool system where it just basically calls for the nearest merger, and it will just remove 3 boxes from that merger. So we use kind of pistons to generate the additional pulse, and it will just dispense exactly 3 items, and then it will the block will be recovered essentially. So the other motivation for this is that the idea is that when this system unmaps, either you'll have like 1, 2, or 3 shulker boxes, or 0 left over, and when it unmaps, the idea is that if you were in the unlucky situation where you have just a 1 remainder, then that box gets sent into this stream, and that's the box that's sent to the encoder. So basically it's like in the double pass system, again I made a video about this, but basically periodically we'll just check for idle slices which don't have enough shulker boxes to send to the 3 mergers, and then in that case basically then we're encoding the boxes essentially, which is pretty cool. So yeah, again, there's a lot of edge cases, and actually like most of the stuff here is actually for unmapping. So this will just periodically come along and find the closest one which is ready to unmap, and then it will unmap that. I'll talk about that a bit later, but yeah, that is why we're using this. And by the way, everything in this video is fully hopper locked, no toggle states, MBE friendly, and also controversially 1.12 friendly. So reasonably well designed, but you can definitely make everything more compact. It's just a proof of concept. Now, you might be thinking, why would you want to make a system like this? And, why would you build one of these 3 mergers over 2 conventional mergers? Because the Hoppy speed's the same. So why would you do it? And the reason is that it's a kind of brute force way of integrating merge optimization into a storage. Because most merge algorithms that are kind of feasible to implement are greedy algorithms. I mean, they're only relevant to kind of just one merger, essentially. And they kind of only work with just sort of given a sort of constant theoretical batch of boxes, and it doesn't make as much sense when considering lots of boxes and sort of coming in continuously. And it also gets tricky when you're trying to sort of make a perfect optimization algorithm, because it's kind of impossible, because if you really worked it out from the initial batch, then in some cases it even makes sense to sort of split a box in 2. You have to do some really strange operations, which is just really not feasible. So it's a way to try to make merge optimization, try to make it a bit more feasible. And why is this optimal? So it's really not obvious why this is better. I'll put a diagram on screen to show that just if you take some random case, very often it will be faster. And in this diagram, you can see that, I'll leave you to sort of work it out, but I've assumed the worst possible optimization for the 3 mergers and the best possible optimization for the 2 mergers. And the 3 mergers are still faster. Just in terms of it just reduces the number of sort of iterations required, essentially. And if you look at the blue underlining, that's the amount of time it would take if you assume the opposite case. So in some cases it can be significantly faster. And the way to sort of know if it will be faster is if you need to think about the asymmetry between the contents of the box around the sort of halfway. So if you have lots of boxes which are less than half and few boxes which are more than half initially, then this is more likely to be faster, because the ratio is closer in terms of the boxes that will be unloaded and the ones that will be loaded to 2 to 1. If you have a situation where it's 90% full, 10% full, 90% full, 10% full, because that's more of a 50-50 situation, in that case the 2 mergers will be more efficient. However, if you think in reality, when you're using splitting, or if you're using a kind of entity-based filtering thing, in that case you actually get a lot of boxes from the splitters. It's much more common to get boxes which have a low number of items in. So in the picture that I've shown, all the boxes are 20% full. And so this is actually quite realistic when you're thinking about splitters. You're more likely to get boxes with less items in them. So it's not like we can't assume a perfectly uniform distribution of boxes coming through at an equal rate. So in the case, it is in this case it is optimal, but it depends on the input method that you're choosing to use. So it's just an alternative approach that can be, in some cases, significantly faster, but other cases it's slower. Okay, so let's check out the system in action. So I'll just switch the clock on, and what I'm going to do is I'm just going to input 27 of a box with exactly 2 stacks. So we're just going to expect two full boxes of each item type. So let me just do that. Okay, so first of all, the boxes just go through this central filter, just determines whether it's full, empty, or partial, essentially. And obviously all of them are partials right now, so they're going up this stream. And as you can see, we have the A-B input thing I showed in the previous video. So they all go through the A input. They go through once and none of the slices get mapped. They come out the end and they go through this stream, so A to B. And they just go back up through here, through the B input, and then we start mapping silos. So we can see we're sort of periodically mapping. I'll just come inside so we can sort of get an idea what's going on. So periodically, there we go, we'll notice a set of 3 boxes being sent. they'll be dispensed down here, and then as I showed earlier, they'll just be dispensed in order. And then we just, yeah, we start merging. So this one's just emptied, but it shouldn't be long before the next set comes through. Just come back over here, actually, we can have a look. So yeah, so we are merging at double hopper speed. See new yellow ones come through. And I'll just quickly show some of the other stuff here. So how do we unmap? Well, every 7 or 8 or so, we can actually catch it here, attempts, we'll send a pulse down here. We basically stop the main input like this, and then we basically have to wait. This is just an edge case, which is a bit annoying, but it can basically be reduced if the silos are smaller. And that will just unmap the closest silo. Although I think in this case, none of the silos are actually ready to unmap. So in that case, we just unlock the main input and we just allow items to continue to be redistributing. This will make more sense if you've seen the first video. But it's essentially exactly the same thing. And then we can see the encoder stream. There we go, there's another set. What I've done is I've just connected the encoder stream straight back up to the main input. Obviously in reality this would go to a kind of temp storage sort of thing, but it just makes it easier if we connect it to the main input, because obviously in this case we know we're not going to get a remainder of 1. Okay, so I'm just tick warping to speed this up, but we can see that we are merging quite well. And I'll just show one more thing I didn't show earlier. We also have a kind of additional storage for shulker boxes which are of a sort of 9th item type or higher. So if we basically run out of item types, which is quite unlikely, but if that does happen, then we go through this line and it just gets stored in this sort of AB silo thing, which I showed in the previous video. Okay, so we're now on our final box, and you can see it's been forced to just merge 2 at the end because there was a remainder of 2. So it is sorting 1 times hopper speed, but obviously this is just a sort of end case. And given our input, we should expect 12 full boxes. So let's have a look, and there we go. So there's just 12 boxes, 2 of each item type, so that's exactly what we expected. I do have one more thing for you, but it's a bit insane, but I just thought I'd show you anyway. This is a 3 merger, but the idea is that this works on its own. You don't need any additional storage or anything. You could literally just have splitters and then this, and that's it. So obviously it does look complicated, but it actually is relatively functional. So yeah, so the idea is that basically, rather than having basically it has an SVAR built into it. So the idea is that it kind of pair searches, or searches for a set of 3 and then redistributes that. And so you would need some external kind of breaker item thing, but it's not too difficult to implement. And the idea is that basically, like, let's say you had 2 shulker boxes coming in, then it would just start merging. But then we have an additional dropper line, and a 3rd one could come in because the SVAR is built in. So it could just be like, oh yeah, this one is red concrete, and I'm a red concrete box, so it will just start merging. But then rather than just immediately like dispensing the shulker box and then like 3 of them are dispensing, it will just regard that as the end of an unmap event, because it could be that this shulker box is like really full and then you're wasting time. So it just sort of counts that as like, it's basically, in that stage, it's acting as if it's like a pair searcher, but for a set of 3. And then it will just dispense them all out. And then again, you need some sort of external logic, but it gets fairly complicated. You also have to be careful about how you lock this this hopper here. So, basically, if you have 3 shulker boxes, then this hopper will be active, and then this will just basically activate this comparator, and then this hopper will turn on, well, be locked. So basically if you have 3, it will just stop searching. If you have 2, then it won't. But then also if you're distributing boxes, we kind of use the svar for both this kind of third searcher input and the main input. So you have to send a kind of periodic pulse through here, which will just kind of lock it as it travels, which allows you to distribute that svar item in the first place. And yeah, so this thing will just sort of cycle between 3 states. And so yeah, this is the case where it's sort of transferring. This is the case where it's unmapped. And then there's one more case, which is when it's in the process of, it's sort of essentially in the process of removing the boxes. So it's important that no more boxes come in whilst it's removing the boxes. Yeah, so that's basically it. Obviously, this is very impractical. I wouldn't really recommend it, but there are some sort of interesting things you have to do. So yeah, lots of edge cases. I mean, here, for example, you can have like, it's possible that 2 end criteria are met at the same time. So if that happens, like for example, if a third box comes through, then that will end it. But it also might be that it fills at the same time. And basically you have this system where like you need to send 2 pulses to remove both the svar item and the additional item from the third shulker box. And so this thing will like, even if it receives 2 pulses at the same time, it will still send 2 pulses. And you have to do things like, to get the hopper locking to work, you can like reuse the svar repeater. So yeah, just lots of strange things like that. Anyway, that was just a little fun thing at the end. But yeah, that is pretty much it. So yeah, thanks very much for watching, and I'll see you in the next video.